So welcome back for the second session of lecture number 1. Now we have discussed what are networks and what are the basic property of networks. Now I want to tell you a little bit about what is the maximum entropy principle, because the goal of this module is to use the maximum entropy principle to construct models of network. So here in the remaining part of this lecture, we will abandon network and we will only speak about, the information theory based principle that we will then be applied in network in lecture 2. So in information theory, you can define an ensemble, and an ensemble is mathematically defined as a triple x, ax, and px, where x is the outcome of a random variable, which can take one of the possible value in the set capital AX, so you can take value A1, A2, AM, and for each of these values, we assign a probability P1, P2, Pm, defined in this set, capital Px. Of course, this probability must be probability, so greater or equal than 0 and smaller than 1, and the probability distribution should be normalized. So really, you want to describe an outcome, and to each outcome you describe, you assign the outcome of a random variable, and to each outcome you assign a probability. So for us then in lecture 2, our outcome will be a network, and then we will assign a probability to a network. This is just to give you an idea of why we do so. Okay. So in general, you might not have just one random variable, but a random variable which is actually is an ordered pair of two random variables, x and y, and then in that case you can define a joint probability for these two random variables, which has a marginal, and the marginal is can be expressed in terms of the joint probability by sum of the marginal p of x can be expressed in terms of the joint probability by summing on the other variable. So you want to know, regardless of the variable of y, what is the probability of observing x. And you can also define a conditional probability using Bayes' rule. So interesting, when you have a random outcome, you can define the Shannon information content of an outcome. And this is defined as hx, which is just minus the logarithm in base c of the probability of this outcome. So here, for the base of this logarithm, traditionally people have taken 2. In this model, we will always take c equal to the Euler number. In any case, if you want to change the base, the Shannon information will change by a factor, So not be an important consequence, changing the value of c. So here, for the Shannon information content, one important thing is that the smaller is the probability of an outcome, the larger is the Shannon information content. And, oppositely, the larger is Px, the smaller is the information content. So if you have really an outcome which is deterministic as probability 1, then the information content is, the Shannon information content is 0. So it describes, in some sense, what is the uncertainty in this value. So the Shannon information content can be also applied to joint distribution, joint ensemble. And if the probability joint distribution, if the two variables x and y are independent, the Shannon information content is additive. So it's h of x minus h of y. So with the Shannon information content, we can define the entropy of an ensemble, which is S is defined like minus px logarithm of px. And so it's the average of the information content of every outcome. And the entropy is defined in this way when if the probability is 0, we use the convention 0 logarithm of 0 equal to 0. So we define this convention. So really the S is the sum of this px logarithm of px, this term, over value of x for which the probability of x is greater than 0. Okay, so now this information, this entropy really encodes the information encoded in the distribution, and as an important property is the entropy is non-negative and is 0 only for deterministic outcome. So the entropy is greater or equal than 0 and is 0 only if px is equal to 1 for one given outcome. So in order to prove that, we can start with the definition of the entropy, which is listed here, which we commented before. And so if we have an outcome that is not deterministic, every outcome will have a probability included between 0 and 1, never 1. And therefore, the logarithm of p of x with a minus sign in front will be positive. And so the entropy will be the average of this Shannon information content, and therefore will be the average of positive term, and therefore will be positive. If the probability instead is equal to 1 for one outcome and 0 for any other outcome, then the entropy will be 0, because it will be 0 or for any the logarithm of px logarithm of px will be 0 for any px which is 0, and when px is non-zero will be 1, and then px logarithm of px will be 0 again. So really the entropy for a deterministic outcome is 0, and in some sense, when it's greater than 0, it measures how uncertainty is encoded in the distribution Px. Another property, and really in order to know what does this number, the number of the entropy, really mean, we can look also at another important property of the entropy, and the fact that the entropy is maximized for uniform distribution. And for uniform distribution, the entropy is just the logarithm of the number of possible outcomes. So if the number of possible outcomes is m, the entropy is maximized for a uniform distribution, and it will take value logarithm of m. So let's prove this result. So we have a set of outcomes which is cardinality m, and the probability distribution is normalized, and we look at the entropy of this ensemble. And in order to find for which distribution this entropy is maximized, we use the approach of the Lagrangian multipliers. So we consider a functional f, which is equal to the entropy, the quantity that we want to maximize. And then we add as constraint the fact that P of X should be normalized. So we add the Lagrangian multiplier nu, and then the constraint which we want to satisfy, which is expressed as a sum of x of px minus 1. So we can explicitly express the entropy. And now, in order to find the distribution which maximizes the entropy, given the constraint that the probability is normalized, we need to differentiate. So we can differentiate respect to nu, and we can differentiate also respect to the, do a functional derivative respect to the distribution. So if you don't know what is a functional derivative, don't be afraid. Here we consider practically every value of P of X. So P, the probability of a first outcome, the probability of a second outcome, and the probability of the M outcome as M different variables, and we differentiate respect to each of them. So when we do the derivative of this functional respect to P of X, here in this sum, we will get just for just one term minus logarithm of P of X, and then we minus 1, and then we will get, when we derive the second part with respect to P of X, we will get minus nu. And we maximize this functional, so we put this partial derivative equal, a functional derivative equal to 0. And so this functional derivative will be equal to 0, the partial derivative will be equal to 0 for every x. And by solving this equation, we find that P of X is just given by a constant, which is e to the minus 1 minus nu. Okay, so we know that P of X is equal to a constant. Now, if we extremize the functional f respect to nu, let me just go back once, show you the functional f. Nu is here. When we derive respect to nu, we get minus the thing in the parentheses. Here, minus the thing in the parentheses equal to 0. And this is, if we put this thing equal to 0, this is nothing else than imposing that the distribution is normalized. So let's impose that the distribution is normalized. Let's substitute to P of X the constant value. When you sum over all the elements of the set of possible outcome, you have M, capital M possible outcome. This is equal to 1. And therefore, we find that this constant is e to the minus 1 minus nu is just equal to 1 over capital M. So we have proven that, the distribution which maximizes the entropy is the uniform distribution, and then we can substitute this into the definition of the entropy, and we find that the entropy is the logarithm of the number of outcomes. So really, this is a meaning of the entropy. It will tell us that the entropy, also when we don't have really a uniform distribution, but the entropy characterizes the logarithm of the typical number of outcomes that we have for a given distribution. Okay, so the more outcome we have, the more is the entropy. The less outcome we have, for instance, 1, the smaller is the entropy. And then if we have just one outcome, the entropy is really 0. So for a Bernoulli distribution, we can calculate the entropy, and it's given by this expression, and interesting as this shape. So if the probability of observing x for the probability p is 1, or the probability p is 0, then the entropy is 0, because we have a deterministic outcome. And if p is equal 1/2, the entropy is logarithm of 2. Okay, so it's and so we have equal chance to have the two possibility, and this is the uniform distribution. So for the uniform distribution, the entropy is the logarithm of the number of outcomes. So the entropy can be defined also for joint ensemble. And if the ensemble, the joint ensemble define an uncorrelated variable, is additive. So is the entropy of the joint ensemble is the sum of the entropy of the associated to the single variable. You know, this is only if they're uncorrelated. So really, we will use this entropy to construct models that are least biased given a set of constraints. So we follow Einstein quote that says everything should be made as simple as possible, but not simpler. And so in the maximum entropy principle says that the least biased ensemble that satisfies a set of constraints is the ensemble that maximizes the entropy under the imposed constraint. So we will use the entropy and its maximization to find ensemble that satisfy given property. So this given property can come from data or from previous knowledge of the ensemble. So if you want to construct a set of an ensemble with given property, and is a very, very powerful tool to construct ensembles starting only for partial data, partial information. So what we want to do, we have some observable, so some function of the outcome. We have P observable, P function of the outcome, and we want to fix their average value over the distribution P of X. So we want to say that the ensemble in average, you know, I'm observing in average, the observable will take value capital C mu for each of the outcome. And if I maximize the entropy given this constraint, I find this distribution P of X that takes this form. This is very general form, and is called the Gibbs measure, in which we have an exponential, and we have some variable here, lambda mu, which are, we will show they are the Lagrangian multiplier of the constraint. F of mu of X are the observable, and we have a normalization constant Z, which is also called partition function. And so Z is defined like that. It's defined by imposing the normalization constant. And these Lagrangian multipliers can be shown to satisfy this relation, so that, you know, they need to satisfy this a relation. So let me go and prove this.
Excuse me. Yeah. I have a question. This is, of course, standard in statistical physics. But is there any, and usually the C mu here correspond to conserved quantities in the physical system. Is there here any example of an ensemble over a network where these charges that are conserved is an infinite set? So you have an infinite set of constraints, let's say.
We will cover cases in which this set of constraints is extensive. So we will go.
Exactly. Extensive is even better.
Yes. So we will.
So there are cases.
Okay. Capture this. So for instance, if you want to fix the degree of each node, you will have a set of constraints which is order n, because there are n nodes.
Yes. Okay, great. Okay, thank you.
So so let me go to the proof. So you have this this constraint. So your observable average over px is given by this value, capital Cm. You have the normalization, which is also always a constraint, and you have an entropy, the entropy that you want to maximize. So you proceed as we did before using this Lagrangian multiplier. So you define a functional, which will be the entropy. And then for each constraint, now we have P constraint, you put a Lagrangian multiplier and the thing that is 0 under this constraint, minus the other Lagrangian multiplier enforcing the normalization condition. Okay, and now we proceed exactly as we did before. So we extremize this functional respect to P of X and to the Lagrangian multiplier, lambda mu and mu. So when we do the functional derivative respect to P of X, we get minus logarithm of P of X minus 1, which we put here. Then you do the derivative of this part respect to P of X, and you get minus sum of mu between 1 and P of lambda mu f mu of X. And then when you derive this last part, you get minus mu equal to 0. When you derive respect to the Lagrangian multiplier, you just have always, you know, the constraint that you want to impose equal to 0. Now, if you just look at the first of this equation as an equation for P of X, you can find out that P of X has this exponential form, e to the minus lambda mu f mu, and has a constant in front. Okay, so really this P of X that we express in this way is the Gibbs measure, and it needs to satisfy the normalization condition. So this normalization condition will define e to the nu plus 1, which is nothing else than zeta, the partition function, as this sum. Okay, so we have proved that the probability distribution which maximizes the entropy given this set of constraints is the Gibbs measure, with the partition function defined as we wanted to be defined. And then when we derive respect to the other Lagrangian multipliers, we find C mu is equal F mu P of X. We substitute, instead of P of X, the Gibbs measure. And when we find this expression that we notice can be also indicated like minus the partial derivative of logarithm of z respect to the Lagrangian multiplier lambda mu. And these are the three equations that we wanted to prove. So this exponential form of P of X is quite general. And in fact, many of the network ensemble that we will construct in this way the network ensemble that will be constructed in this way will be called exponential random graph, because they will have this Gibbs measure structure. So here I leave you for as an exercise to show that actually, given this Gibbs measure, you can calculate the entropy, and that the entropy takes this simple form. So it's expressed in terms of the Lagrangian multiplier, the expected value of the constraint imposed plus the logarithm of the partition function. Finally, and this I conclude this part, and then maybe you know, later, if you want, I can give you more detail about this derivation if you want, because these are very important aspects that we will use also later. So here I want to tell you a little bit more about what really what is the implication of what we mentioned, and in particular, how can we take the constraint? Okay, so this is an alternative way to show you that this constraint can be taken starting from data. So here the approach will be different. So we start with some data of the outcome of some random variable. And we assume that the probability of this random variable follow the Gibbs measure with some parameter lambda, which we want to find out. We want to find out the best parameter which describe the probability distribution that characterize our data. So in this approach, what we are interested on is what is called the log likelihood. So the log likelihood of a parameter given a set of data is given a certain value of the data is minus the logarithm of the probability that this value has in a model which use this parameter lambda. So we have a set of data, outcome of our variable x, x1, x2, xn, and you have the likelihood of this set of data, and then for each it's the sum over I, so for over all the data sets, the data that you have, of minus the logarithm that this value is observed in your model, that is a model which describes the data with the probability p of x, which is parameterized by some variable lambda. Really, you want to know which are the best lambda, which is the best distribution that describe your data, and in particular, which are the best lambda, because you restrict yourself into a class of model that is parameterized with lambda variable. So you want to know which is the best lambda that describe your data. So you want to find the lambda which maximize the log likelihood of your data. In order to do that, you consider, for instance, trying to be quite general, you consider as possible distribution of your variable a distribution which is given by Gibbs measure, which have Lagrangian multiplier lambda mu, okay, and which multiply given set of observable. You might want to use several observables. So really, if you want to find the parameter value which maximize the likelihood, you find actually that these optimal parameter are found by imposing that lambda are the Lagrangian multiplier of a maximum entropy model, in which the constraint is given by the expectation that your observation, the average value that your observable take on the actual data. So, if you want to have a model for a given, I don't know, observable, for instance, a temperature, you want to take as constraint the average temperature you see in the data. Or in a network, if you want to have an ensemble of network with given number of links, then if you have a given network, the most plausible ensemble is the ensemble that characterize your data is an ensemble of network in which the number of links is exactly equal to the one that you observe in the data. So in order to do that, we can consider a given set of data set, the log likelihood of the parameter lambda given the observation, which is given by this term, which we discuss, we take for P of lambda x the Gibbs measure, and then we can just work out for this Gibbs measure what is the expression of the log likelihood. Okay, so this is the logarithm. You use the definition and you insert the expression for P lambda of x, and you find that is given in terms of lambda mu, which are the parameter you want to find, the observable calculated in the data that you have, plus n times the logarithm of the partition function. Now you have this log likelihood, and you want to find the lambda, the value of lambda, which maximize this log likelihood. So you derive respect to each lambda mu. And when you derive the first term, you get just the observable calculated on the value that you are really observing. And so these are the value of the observable calculated on your data, plus n, the logarithm, the derivative, the partial derivative of the logarithm of the partition function respect to the Lagrangian multiplier lambda mu. So here you reorder this last equation dividing by n and putting this partial derivative on the other side, and really you find that this minus the partial derivative of logarithm of z of respect to the Lagrangian multiplier lambda mu, which is the average of the observable in the ensemble, should be equal to the average of the observable in your data. So really, if you have a data, this log likelihood corresponds to a maximum entropy in which the constraints are fixed by the data. And this can guide you in choosing the best constraint for your example. So for instance, if you have some data about some network and you want to construct in general the class of network from which this data can be thought to be extracted, you will consider as a constraint the constraint that you can observe on the real data. So for instance, you can consider the same number of links that you observe in the same number of data, or you can say you observe the same degree sequence that you observe in a real network. So here I reach my conclusion for today. So I show you in this first lesson, we have covered an introduction to network in general. What is a network? What is an adjacency matrix? What are the universality property and the degree distribution? And then I have presented you this maximum entropy principle that is a fundamental property in information theory, and as your colleague has noticed, is also very used also in other disciplines, including physics and statistical mechanics. And in lesson 2, we will merge these two topics, and we will speak about using maximum entropy principle to really model network. So thank you so much for your attention. Let me just stop the recording and we can start the discussion if you want.